Okay, we're going to talk about the Arrhenius relationship. I tend to say Arrhenius. I'm pretty sure it's Arrhenius. Not too committed to it though. When we talk about speeding up a reaction, we usually talk in terms of we can increase the concentration of something, which will increase the rate because it'll be proportional, or we can change the K value. And there's different ways we can change the K value. The K value depends on temperature, activation energy. It's also going to depend on something called the frequency factor, depends on the frequency of collision. It tends to be something specific to a given reaction. Mathematically, K equals AE to the negative EA over RT. In this equation, per usual, temperature is going to be in Kelvin. Activation energy, you need to be careful for any equation derived from this. It needs to be in joules per mole. R is 8.314 joules per mole Kelvin, and the units of A can change. A more common form of this equation that we usually see, oh, sorry, let me go back. So with temperature, an increase in temperature is going to give us an increase in the rate constant. For activation energy, because we have a negative exponent and it's in the numerator, a decrease in activation energy, like with a catalyst, is going to give us an increase in the rate constant. And these aren't linear changes. A common form of the equation that is used is this one. ln K1 over K2 equals EA over R times the quantity 1 over T2 minus 1 over T1. For your test, this is the form of the equation I'm going to give you. So we need to be careful here with units. EA, again, needs to be in joules per mole. R is this R, the universal gas constant. Temperature needs to be in Kelvin. You need to be sure to look at for the distinction between lowercase k's and capital K's or capital K's. Lowercase k's are your rate constant, capital K is your units on temperatures. So if this allows us to relate two different rate constants or two different rates at two different temperatures. K1 over K2 is the ratio of the rate constants at two different temperatures, or it's the ratio of the rates. So in other words, if we say a reaction is 3 times faster, we know the ratio of one rate constant to the other is 3 to 1. So let's take a look at our first sample here. A reaction has an activation energy of 250 kilojoules per mole. At what temperature will the reaction be twice as fast as it is at 27 degrees Celsius? So different ways we can approach this. I'm going to copy my equation down here. So the first thing we should think through is the second temperature going to be higher or lower than 27 degrees Celsius? So 27 degrees Celsius is going to be the slower temperature because I want to know at what temperature will be twice as fast it is 27 degrees Celsius. All right. Um, my faster temperature, I'm going to use a K of 2. And for my slower temperature, I'm going to use a K of 1, giving me a ratio of 2 to 1. You need to be careful that your K that's here matches up with your temperature that's here. So if I used this K here, then am going to match it with my unknown temperature of X. For the other one, 27 degrees Celsius is going to be my lower temperature. Need to make sure that that's converted to 300 Kelvin. And then that matches up with my slower K value of 1. And these Ks aren't really 2 and 1, but I know the ratio of one to the other of them is 2 to 1. All right, activation energy is in the wrong units. Before I plug it in, I need to convert it to joules per mole. And R is 8.314. All right, so I've grabbed a calculator. On the left-hand side of the equation, ln of 2 over 1 is going to give me 0.693. I'm going to solve for 1 over T1. Okay, so now I'm going to take 0.693, or ln of 2, and multiply by 8.314 and divide by 250,000. Next step, I'm going to add 1 over T1 to the other side. So 1 divided by 300 minus answer. So T1 will equal the inverse of that. And I got an answer of 302 Kelvin. Perhaps I didn't set up the most feasible question here. The higher the activation energy is, the more the rate is going to speed up with changes in temperature. And so we ended up with a pretty small increase in temperature here of 302 Kelvin.